Stephan, thanks for joining today. We're looking forward to hearing what you're working on. Let me just share a little bit about our speaker, Stephan Zheng. He's leading the AI Economist team at Salesforce. And his team is using deep reinforcement learning techniques and economics simulations to basically come up with better economic policies. Stephan received his PhD from Caltech, and his research was published in very large media outlets like Financial Times, Forbes, MIT Tech Review. Stephan, thanks for your time. We really appreciate that, and we're very much looking forward to learning what you're working on.
Yeah, thanks, Sophia, and thanks everyone here for coming. Yeah, it's a great pleasure to just talk to you about this work. And Sophia told me that it's very informal, so feel free to interrupt me. And yeah, I guess Sophia can be the host and sort of direct or allow you to unmute yourself and so on. But yeah, just feel free to ask questions. And I kept this presentation relatively short, so there should be more than enough time to ask questions, at least half an hour for questions. Yeah, and so this work is about the AI Economist. As Sophia explained, it's trying to use AI to devise better economic policy. So in a nutshell, this is the first reinforcement learning tool for tax policy design, although it can be used for general forms of economic policies. So we can think about subsidies, laws, and so on. It uses simulations and data to learn economic policies. And then what the simulation lets you do is testing and accelerating the design of economic policies. Now, the high-level part of this is that we hope that it improves social welfare on a global scale. So that includes things like equality, economic productivity, and also transparency around economic policy making. And in this talk, hopefully, I'll explain how that works and to give you an impression of the work that we're doing. So as background, so many people probably read about the economy at some point, right? If you read a newspaper or if you listen to the news, most of the time there will be some news about various aspects of the economy, right? Like, are the economy growing? Are people consuming enough? Are we, what's the budget deficit of the government, and so on. And so really, if you look at this picture on the right, the economy is this very complicated network of businesses, consumers, the government, all kinds of resources that are being converted in supply chains. And it's a very complicated system, right? And for many reasons, we need to come up with policies that regulate and govern this entire process. Right? It's very complicated. There's many forms of policies. And so if you ask how a policymaker could improve economic outcomes, so basically, how much money do you have to spend every month? Very often it's really hard to do that, right? To design good policy, because there's simply not enough data, fine-grained data about people's behavior in the economy. And economists very often use very simple models of how people behave, how companies behave, and the effects of, for instance, raising taxes or lowering taxes. And that's simply very limited. So economists cannot model this economy, this network as a whole. Like very often they just take very small parts of it and then say, well, everything else doesn't matter. We're just going to study a very small part of this economy. But for very obvious reasons, that's very often just way too limited. And the third problem is that it's really hard to experiment in the real world, right? The real world is not some sort of lab with test tubes where I can just isolate the thing that I'm interested in. A real economy is this very interconnected web of activity, and it's really hard for any government to to sort of mess around with the tax policies, for instance, and then just observe what the outcome is. So in short, economic policymaking is really, really hard. And on the other hand, there are many social issues that affect all of us that are actually a growing source of concern. And one of them is income inequality. So on the left, you can see in a chart that incomes in the US have grown far apart in recent years. So if you look at the top 1% of incomes in the US, you can see that their income has grown 2.5 times almost in the past 25 years. And if you look at the bottom 20%, it's grown less than 50%, right? So that's a big gap that's been developing. And this happens globally as well, though it's not as dramatic as in the US. And incomes are not the only source of inequality. There's wealth inequality, there's inequality of education, access, and so on. And this is a big concern. But again, it's unclear what the effect is of any policy that tries to improve this situation. So specifically, what I wanted to show you today is how you can design better tax policies using AI. In tax policy design, there's two things, equality and productivity, that are basically being balanced by a government. And why is that? Well, it's because you can use taxes simply set to take money from the rich and give to the poor, right? But you can't take too much money because then you disincentivize people from working. So what's happening here is that on the one hand, you can improve equality by doing this wealth transfer, but on the other hand, you don't want to transfer too much wealth because then you make people too unhappy, right? So every choice of tax policy is going to give you some combination of equality and productivity in society. And the goal is to get as close as possible to the so-called Pareto boundary, which is the set of points where you can't do better along one dimension without sacrificing along the other dimension. So the goal is to get as close as possible to the Pareto boundary and also have control over where you are on that boundary. Right? This is a very fundamental trade-off in economics, and we'll see that the AI Economist comes up with a tax policy that basically gets closer to this Pareto boundary than the three other baselines. The free market, in which there's no taxes at all, the U.S. federal system, which is a progressive tax schedule, as we have in the U.S., and then the SAS formula, which is the economics model for optimal taxation. And so really there's two ingredients, as I mentioned at the beginning. There's simulation, and then there's reinforcement learning. And so first, as a simulation, that's what's visualized here, we have this two-dimensional model. And this is really simple. It looks like Pokemon. And this is intentional because as AI researchers, we focus a lot on how to make that AI part of this policy design framework work. But this simulation has 4 agents. So you see that they're running around, and each agent can collect resources like stone and wood. And they can also make money by building houses. So every house here gives every agent some amount of money. But the one crucial difference is that not every agent makes the same amount of money from building a house. So you see that the orange guy is incentivized to build a lot of houses because it's building a lot. But then some other agents are more incentivized to actually sell their resources to that agent in the middle because they don't make as much money from building a house. And on top of that, like, these agents are paying taxes and they get subsidized by the government, who's again doing that wealth transfer. So one thing here is that this is actually already much more complicated than some economic models that tax policy or tax economists consider. This is very strange. This looks like a toy world, but mathematically it's more complicated because it involves things like trading, right? These agents can sell resources to each other. The simulation evolves over time. And this is a big difference with classic tax models that basically consider worlds where there's no time, essentially, and where there's no trading. So the funny thing is that this simulation is already more complicated than what a lot of traditional tax models would consider. So here's sort of a breakdown of what's happening in this world. So on the top, you have this a couple snapshots of what happens in the simulation. And in the middle, you can see how some key economic observables are evolving over time. So these agents, as they are moving around in this world, collecting resources, building houses, they're working, right? So they're actually spending energy on, chopping wood and collecting stone and then building these houses. And so you can see on the left plot here, labor in the middle, that the orange agents working a lot, and then the blue and the yellow agents are also working, but perhaps less so. And then, in fact, this orange agent works a lot because he's building a lot of houses in the simulation. Build houses is house building is more costly in terms of labor than gathering resources. And in the middle, you can see that the orange agent is also earning a lot of money, right? More so than the other agents. And then on the right, you can see that the orange agent also experiences the most utility. So utility is a measure for happiness. That's the common definition used by economists. And so every agent here in this world is basically incentivized to maximize its utility. And utility is basically a balance between earning money, that gives you positive utility, and labor, which costs you utility because you have to work, right? And as you can imagine, if you work a lot but you don't get paid, then you're not as happy. And in the bottom row, you can see that the trading also happens here in the simulation. So the first three agents here are earning money because they're selling resources. So the bars here are pointing upwards. And then in the fourth agent, you can see that that agent is buying resources. So it's losing money, but it gets resources in return. So as I mentioned, all these agents experience these economic drivers. They work, they make money, and they experience this utility. And one quality of this utility is that it diminishes over time, in the sense that the marginal utility diminishes over time. So as you work more and more and more, the extra amount of money that you earn makes you less and less happy, right? And so this encodes the idea that everyone, to some extent, works, but not everyone might be equally incentivized to work more. So some people might work on the weekends because it's really worth it to them for some reason, but other people might not do so, right? So this is like a law of diminishing returns. And the second thing that's really interesting is that as a result of these economic drivers that these agents experience, and now we're using AI to optimize their behavior, you see that there's specialization that emerges in these agents, right? So one interesting feature about these AI-driven economic simulations is that these agents learn that based on how much money they can earn by building houses, it's more profitable to sometimes sell if they don't make enough money for every house they build, right? And so this emergent specialization is something that emerges because of these learned behaviors of the agents. And this is also a big difference with what people do in classic economic tax models, where people don't consider these types of economic features as emergent from the behavior of individuals. Rather, it's some sort of assumption that they build into the model, which makes those traditional models much more rigid compared to like the simulations that we have. Okay, so why I'm showing this to you? Well, I'm trying to convince you here that these simulations that contain these economic agents that are using AI models to model their behavior using these economic drivers, basically it's a much richer way of simulating economies. Even though this looks very simple, if we scale this up, basically we will work towards the simulation of the real world that's much better, a better tool for economists, because now we can use these simulations to test and evaluate any sort of policy in a simulation. And then if we have agents that are realistic enough in their behavior, we can see how the economy as a whole responds to different policies that we might impose on this economy, right? And that's the first pillar for this economics research. So the other pillar is this AI part, right? I spoke about, okay, well, these AI agents are behaving in a certain way, and the technique that we use is reinforcement learning. And we use reinforcement learning both for the agents and for the government on top. And that makes it so-called two-level reinforcement learning. Now, reinforcement learning is a general machine learning technique. I'm not sure how familiar this audience is. So here's a slide that summarizes the flavor of reinforcement learning that we use in our work in this project, and it's called On Policy Model Free RL. And so the idea is that every agent basically has a parametric policy in mathematical notation pi sub theta, and this theta are the weights, the parameters of this model, and this model is computing a set of probabilities over all the actions for every agent. So you saw the agents move around, right, and build houses. So every agent can choose to move or choose to build a house. And this pi sub theta is going to assign a probability to all of these actions. And these actions probabilities are based on a state, S sub t, right? So every agent at some point in time can look around in the world and see, oh, there's some wood and stone close to me. So then because of that, I'm going to choose to do a certain action. Oh, oops, sorry. And so what does reinforcement learning do? Well, there's basically two steps. You first take this policy model. You're going to execute this in a simulation. That means that you're going to basically see this little movie reel of these agents running around. That means that they're using that policy to sample some actions, and their environment tells them what's going to happen. And then you collect this trajectory, this like movie clip of what happened in a simulation. And then you're going to compute this gradient that updates the parameters of your model. And the gradient is the one that maximizes the expected return for this agent. So every agent experiences some increase in utility, right? Becomes a bit happier because of its behavior. And then mathematically, you're trying to change these thetas in such a way that you push up that expected happiness that you experience. So you can derive the gradient as of this form as I show here. And the idea is just that you say, well, if in this particular rollout of the simulation you did well, so you experience a lot of utility, then you should do more of that behavior, right? So for instance, if an agent makes a lot of money building houses, then this gradient basically tells that agent that the agent should go build more houses, right? But if an agent experiences a lot of profit from selling wood, then this gradient says, oh, you should go sell more wood next time around, right? And so in this way, these gradients are changing these parametric policies for different agents. And this process just repeats over and over and over again, right? So the reinforcement learning is smart trial and error, right? Every time you try out like your current policy in the simulation, you see if it's better, and if it's better, then you do more of that behavior.
Stephan, I just would like to clarify. So each agent gets different rewards for different kind of labor. How you like assign the rewards for agents? Yeah,
exactly. So every agent, it completely depends on what it does, right? But some agents make a lot of money, so then that gives them utility. Some other agents make a lot of houses, that gives them utility. That reward is something that the simulation assigns to that agent, right? That the simulation computes for that agent. So yes, it's going to be dependent on what the agent does, and it depends on the characteristics of that particular agent. Yeah. Okay, so hopefully that sort of at least gives you the intuition, right? And so if you assume this as a black box, right, the critical step here now is to define this reward function, right? So we have the simulation, we have this parametric policy. So now as if you're a machine learning practitioner, right, you have to define the reward function. And so as I mentioned, for these agents, we look at the utility that they experience during the simulation, during every episode. So these agents are going to try to maximize this expected sum of rewards, and every reward at every time step is the increase in the total utility that this agent experiences, right? And that utility is the sum of two things. So it's dependent on the income X, raised to some power, and we subtract the labor linearly, right? And if you think about labor as a one-dimensional thing, this particular utility function looks like that on the right. It has this sort of hill-like behavior, right? So in blue, orange, and green, you see three versions of this utility function, and the difference here is in the skill. So skill measures how much money you get for a certain activity. So for a higher build skill, right, means that you get more money for building a house. And so the idea here is that the more skilled you are, the higher the utility is that you're going to experience, and therefore the more incentivized you are to work longer hours, right? And then a crucial aspect here is that the income X is the post-tax income, right? So everyone pays taxes. So let's say I make like I don't know, it's like $100,000 by building a house. I have to pay taxes over that, and those taxes here are denoted by capital T in the bottom, right? So yeah. Now the same thing is true for the government, right? So there's a government on top. You know, these taxes are basically being set by that government agent, and so the government also has a reward function, and a reward function in this case is equality times productivity, and you know then the instantaneous reward is the increase in this product between equality and productivity. And that's basically to incentivize the government to go towards this Pareto boundary. So if you think about it, the reward function should increase towards the Pareto boundary, right? And yeah, like that product of equality and productivity is one such function. Now productivity is just the sum of all the incomes X, and then the equality is 1 minus the Gini index. And so the Gini index is one way to measure the differences between incomes. It literally is the normalized sum of differences. So you take every pair of agents, you look at how much they made, you compute the difference, and you add up all these differences. Yeah, then you get the Gini index. Okay. Now, important here is that, as I said, as a designer, you set the reward, right? So imagine you're like the government. You can actually choose what social welfare means to you. And in that sense, this framework is very flexible, right? And this opens up the discussion to, well, as society, right, if we use the system in the future to recommend some form of policy, we better think very carefully about what the reward actually includes, right? So I talk about equality and productivity, but you could include many other things that matter to society, right? Sustainability, social mobility, helping the middle class, and you can, you know, have a whole list of things that matter to us. And so a big question is, well, you know, in the future, if we have better simulations, what are the right reward functions that we should use for the system? Okay, so now I wanted to, well, show you at least like a sort of schematic of what happens with these parametric policy models. So we use neural networks to implement these policies, and these neural networks are basically observing the world, the state of the world, in a number of different buckets, because there are many different types of information in the simulation. There's a public map, which is the geometric information. Then there's a public state where every agent can see the tax rates and you know, the state of the market, like who's selling wood, who's selling stone, and so on, and what are the prices in the market. Every agent can see what it owns, its endowment, and every agent can see how much it's worked and how high its skill is for certain activities. So the agents know that they're very good at building houses, or that they're very good at selling things, for instance, or collecting things. Now, an important distinction here is that the government cannot see all that information. That's why you know, some things are so-called private. So the government cannot see how much you've worked, and it can't see how good you are at something. And this is an assumption again in economics that it's actually really hard to pinpoint how quote unquote good people are at things. And the government can really only see things like how much money did you make, right? And sort of what's your occupation, but it's really hard to sort of put a number on, you know, people's skill. So that's why it's often considered a private hidden variable. And a semi-private state means that the government can see, for instance, how much income you've earned, because that's a proxy for your endowment. But agents cannot see each other's endowment, just like I don't know how much money people make, or at least not like for every individual. And it just adds to the richness and also some a level of realism to these economic simulations. It's really important to consider what information is visible and what is not. And so both the agents in the bottom and in the planner use these neural networks to compute these probabilities for all the actions that they can take. So once we have these policies and these reward functions, now we're going to train the system simultaneously, right? So these economic agents use reinforcement learning, the government uses reinforcement learning. So that's two-level. And so in this schematic, you can see the setup here. So every loop here in red and in black represents this iterative reinforcement learning loop that I explained to you before. And the special feature of this two-level setting is that the actions of the government change the reward function for the agents. So as you remember, the agents are trying to maximize utility. Utility depends on your post-tax income. So it depends on the tax rates that are being set by the government, right? But those tax rates are in turn decided by this parametric policy model that the government uses. And the government's changing its policy model. So what's happening in this two-level setup is that as the government is learning, it's changing the optimization problem for the agents in the middle, right? And this basically is the same thing as that what happens with GANs when people train generative adversarial networks to generate images. You also have two things that are learning. There's a generator for the images, and then there's a discriminator that's changing the objective function that tells the generator if their images that are being generated look realistic or not, right? In the same way, the government here is changing the objective function for the agents in the middle. And as you might know, this is a really hard machine learning problem. So what we see during training is the following plots that look like this. So what I'm showing you here is equality times productivity, the social welfare metric, and how it changes during training. And so this is the training when both the agents and the government are learning. And if you look at the green curve here for the AI economist, you can see that social welfare increases in the beginning because the government is just changing the taxes, finds a way to improve social welfare, but then social welfare goes down again. And that's because these agents in the world are responding to that change in tax rates. So they might try to change their behavior. And so they individually might become happier, but then society as a whole is less happy, according to this metric. And then what happens is that the government, in turn, then again finds a different tax policy, and then you see that the system then starts to converge towards some solution where these two things are balanced out. Like the agents and the government are both happy with their experience reward, right? But this up and down behavior is problematic, right? And this is after we've basically used a number of learning strategies to stabilize this two-level reinforcement learning process. So there's three things that we've done. So there's two-phase training, there's curriculum learning, entry regularization. So two-phase training means that first the agents train by themselves without a government, and then after that you bring in a government to start training them. This gives the agents some time to actually understand how the world works before they actually experience paying taxes. The second is that you need to do curriculum learning where you anneal the cost of labor and the cost of taxes, because in the beginning when the agents are very, they don't really know how the world works, they might work a lot but not actually earn any money, right? I can run around for a long time and not build any houses. I've worked a lot in that case, but I didn't actually make money, right? So you need to slowly sort of increase that cost of labor to let the agents explore and then understand that what they need to do in order to earn money. And in the second phase, something similar happens with taxes. The government shouldn't tax agents at 100% right away, because that takes away all the money they've earned, right? And then you're back in that problematic situation where agents can work a lot without actually earning money for that work, right? So again, you need to slowly turn on the taxes to avoid discouraging these agents from working. And then in the third trick for entry organization, basically that's a very common technique, but in this case, you need to carefully tune this entry organization between the agents and the planner to encourage them to keep on exploring, even though they might experience some cost of labor or taxes. And you need to give these agents enough time to find that type of behavior that actually yields them enough income, right? So we found that this is actually important to balance between the two levels. Okay, so I talked a lot about this AI part, and then so what do you get in return? So let's look at some results. So what you get is like some interesting movie clips that you can make. So on the left, you can see the world in a free market, and the pie shows you how the income is distributed in this world. So the dark blue agent earns about 2/3 of all the money in this setting. And to remind you, in a free market, there are no taxes at all. On the AI Economist, there are taxes, and you see that now the dark blue agent makes just a little bit over half of all the money in this world. But when I look at social welfare, we get a much higher score, about 1,700 compared to 1,200 something in the free market, right? So we have a more equal distribution and higher social welfare. And this is not just true for the video clips I just showed you. This actually happens under many repetitions and many random seeds. And so we improve over 16% compared to the FAS tax, and even more compared to the free market and the US federal tax system. And as a sanity check on the left, you can see that if productivity is always highest in the free market. So any form of tax is going to lower total productivity because you're always going to disincentivize some people a little bit from working more. But the profit that the return, in return, you get higher equality, right? So in the middle, you can see that the free market is the least equal, and the AI Economist achieves the most equal society, right? And together, that gives you the highest social welfare. Now, this slide shows you how this tax schedule actually, what it actually looks like. So in pink, you can see that progressive schedule that the US uses. In blue, you see the schedule that this mathematical model called the SAS model predicts. Well, it's different, it's regressive. And in green, this is what the AI Economist comes up with. And now the way to interpret this is that for every income, or for every sort of income bucket, we predict a tax rate, so we say, for instance, between 84 and 160 coins of income, you need to pay about 60% in taxes. That's quite high. It's much higher than the other tax models. But then in the middle, you pay a much lower tax rate compared to the other models, right? And then again, it's high at the top end. Now, the important thing is that the tax money that is being collected gets redistributed among all the agents equally. So once you take these subsidies into account, on the right, you can see that the wealth transfer, the net wealth transfer, is actually highest under the AI Economist, right? And that leads to the highest social welfare that I showed you before. So the thing about this is that this tax schedule is obviously a bit counterintuitive. It's not something that traditional tax models really predict. But it's because of the flexibility of this reinforcement learning framework that we can really exploit the entire space for all possible tax policies. And in contrast, the traditional tax models are more constrained in some sense. Like they don't allow for a very flexible functional class of tax schedules, and therefore, they're more limited. So another feature of this AI-driven framework is that basically, these agents don't like to pay taxes, right? Because it lowers their income. Just like in the real world, people don't really like to pay taxes, right? I don't, at least. Well, the question is whether you get something in return for it. But most people, I would argue, don't really like it when they, pay taxes. And so these agents, they try to find strategies to lower their tax burden. And so in green, you can see that during a simulation, agents find a strategy where they basically report high incomes in some years and low incomes in other years, right? And on the right, you can see that if you compare this to a strategy where you just do the same thing every year, you actually pay less tax. Now, the way this happens, this way this can happen is that agents can basically save up resources in 1 year and not build houses, right? And then only build houses a lot in some other year. And that basically allows them to profit from the low tax rates in the higher brackets, right? And this is a strategy that these AI agents can find. And what's really important here is that these traditional tax models don't account for this type of strategic behavior, right? Because as I said before, one of these, the canonical SaaS model, basically does not take time into account, right? It assumes that the economy is just like the same every year. Okay, now one other interesting thing that we did was, and this is sort of a preliminary experiment, but we also asked, well, what happens if people are in the simulation, right? Like, what do people do if they earn money? And so again, you get some funny video clips, right? So on the left, you can see the AI agents in the free market. On the right, you can see what real people do in the free market. So we have this Amazon Mechanical Turk experiment. We built a web interface, and we asked 4 people to go control. Each controls one of these agents. They actually get US dollars for every house they build. And you see that agents, or real people on the right here, they behave very differently, right? The dark blue agent tries to block off its bottom right quadrant. People build houses in patterns that are really adversarial. Really, it's very clear that people try to block other people. They're not very cooperative, right? Because you shouldn't take my money or something like that. And what this really shows you is that there's still a gap between the behavior of these AI agents and the behavior of real people, right? And this is another area for future research. But what we did see is that if you take one of the tax schedules that we found using the AI Economist, you again find that social welfare is improved. So this is kind of interesting. In a very small scale lab study, these tax rates that are found by the AI model are actually effective. Now, the caveat here is that because of this behavior that real people exhibit, which is adversarial, but also not consistent, because people, they change their behaviors over time, the variance in the outcomes is much higher, right? So the black bar here shows you the statistical variation, across this, in this experiment. You see that the outcomes fluctuate much more. So this is something that for future research, like, we have to account for, right? Because if we really want to make a system that is effective in the real world, we will have to account for all these issues that we can see in the small lab study. So this is my last section. So I've given you a very brief overview of this work. And moving forward, really, we want to see this as like a new toolkit for economists, right? Economists, broadly speaking, don't use AI. They don't use reinforcement learning. They're not used to thinking about AI as a model for human behavior, right? Or for any type of behavior, really. And so what we want to do, right, is to build more realistic simulations, right? So not this Pokemon world, but something that looks more like the real world that actually is grounded in real world data. We want to think again about what are the right reward functions for society, right? Like what kind of definitions of social welfare can we study? And how can we actually use these AI policies that we find in the simulation and use them in the real world, where we account for the fact that people don't behave like AI agents, right? Or where people are inconsistent and so on. And for AI researchers, we basically want to motivate them to further develop the core reinforcement methodology, to think about algorithms and mathematical techniques to bridge the gap between the simulation and the real world. And also to think about things like how we explain the decisions that this policy model recommends, right? Why is it that this tax schedule is so different from the progressive and the regressive schedules that are predicted by either academia or used in the real world? Well, why is that, right? Because that ultimately serves to build trust in these kinds of systems in the future. And since this is a developer community, like I would encourage everyone to take a look at the GitHub page. So we did open source this Pokemon type world that I'm showing here. So take a look there. You can download it, play around with it. I'm happy to hear from you all what you can do to expand on that. Here's some more resources. I'll point out that there's a website here, mlforeconomicpolicy.com, that basically contains the recordings for a workshop that we organize at NeurIPS. So NeurIPS is like a very big AI conference, the biggest, I believe. That's how it's promoted. And last December, we had a workshop there on getting economists and machine learning researchers in the same room and have them talk about what the future is for this line of research. So if you're interested, you can take a look there and sort of see if you like what they say or not, and then let us know if you don't like it. I'll just stop there, and then happy to take any more questions.
Awesome, thanks, Stephan. So people can actually interact with that world, right? So basically, it's available on GitHub.
Yeah, exactly. So all the videos I showed you, you can use that code to generate your own videos and to train your own agents.
Okay, awesome. Let me go through questions. So Preet is asking, is it built with NetLogo?
No, NetLogo is like another language that's used by the Santa Fe Institute, I believe, but this is like pure Python.
Okay. So Neeraj is asking, what is the role of water in this simulation? Why it's in a geographical feature?
Oh, it blocks people from crossing. So it's just for us to, to create some barriers, basically.
Okay. So the question is about the development of specializations. How much of that is based on the difference between agent rewards for different types of work?
So that's a very good question. So specialization occurs because not every agent makes the same amount of money for a house. So if you remember the orange agent in the video clip I showed earns a lot of money for a house, right? So it experiences a lot of utility for building a house. So let me go back to this one. This one. So that specialization occurs because utility just depends on the amount of money you make, right? And so the orange guy makes a lot of money for building houses, but that light blue agent in the bottom right does not make a lot of money for building a house. So that light blue agent makes more money by selling its resources, right? So that's why you get that specialization.
Mm-hmm. So I see a question from Arman. Are prices and wages in this simulation free, determined by supply and demand?
What is the prices and wages? So the wage is not free, because the wage, the amount of money you get for building a house is set by your skill, which is set, like that's sort of fixed. But the prices are set by the agent. So every agent in this world, when it sells something, it can also ask a certain price for it. And then there's it's kind of like how it works in the stock market. So I want to sell something for, let's say, $10, and the other person is willing to buy it for 11. Then a trade happens, and the price that is used depends on who came earliest. So if the seller came earlier, then it becomes So if the seller comes earlier, it's 10, and then if the buyer comes earlier, then it's 11, basically. So that's market driven.
Mm-hmm, mm-hmm. So I see a question from Paul. I just don't understand what slide he is referring. He said, he's clarifying, is it hours per week? And he's trying to not work more than 168 hours a week.
Yeah, this is more than just a week. This is I need to think about what measure we use for this. I believe it's more than a week basically. That's the hours here. I believe it's like a month, or maybe it's actually I have to look that up, but it's more than a week.
Mm-hmm.
I wanted to look too closely at the number of hours here. The idea is just like that, you work more as your skill increases.
Question from Julian. Did you add any bias based on the gender, or if a person has disability?
No. All people are the same except for their build skill.
Mm-hmm. 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 So question from Preet, what negative effects could you see from higher taxes for lower income brackets? How would you model this?
Yeah, so presumably the reinforcement learning agent has seen it at some point during training. And my guess is that higher rates in higher taxes for lower income brackets, what negative effects do you see? Mm-hmm. Well, the thing is that, ultimately, the net effect is, you have to take the subsidies into account, right? So this is a counterintuitive point, is that, yes, everyone says, oh, taxes are higher. So if people are not aware of the fact that they receive subsidies, right, then it could discourage them from working, right? Because it's really after subsidies that you see that you get more money back under this system where, it's like what AI Economist predicts. And that's only in a simulation. So one thing you could try to do, right? You can say, well, what do people pay attention to? And this is something that people also do in economics. It's called rational inattention, where basically they try to model the fact that people have all kinds of cognitive biases. So, you can ask, like, how much attention people even pay to taxes at all, right? Or do people pay more attention to taxes and less attention to subsidies? Right. And so, if you're interested in that, you can try to play around with those kinds of attention models and say, okay, well, what is the effect of these policies on a behavior? Because the end effect is that perhaps a change in subsidies doesn't actually change people's behavior as much as a change in taxes, right? And so that makes certain policy levers more or less attractive to the government to use.
So here's a question from Anthony. Can you comment on information observable to agent and government? Basically, he's wondering if the setting is a markup decision process or partial observable decision process.
Yeah, it's a POM-DP because it's even worse than a POM-DP. It's like a decentralized, a POM-DP refers to an agent who can only see part of the state of the simulation. But because we have multiple agents here, there's several generalizations, I think, in the theory literature around like DEC MDPs and DEC POM-DPs and so on. And POM-DP plus, like DEC POM-DP plus or something like that, if you like theory. Yeah.
So question from Paul. So basically, based on the difference how human players, act from agents, would you consider modeling the behavior of neural network agents trained from human players?
Yes, that's a future research, something that we've thought about but just haven't had time to do. But yes, there's like a number of things that you can do. You can do imitation learning, so you can say just do supervised learning on the trajectories that you get from people, right? And then you just fit your policy model. You can also try to infer the reward function that people use. So this is called inverse reinforcement learning, and those things have been done before in other contexts, right? But we haven't done it for this work. But yes, that could lead to more realistic fake humans, basically, in the simulation, right? One question is, can you train AI agents to be more like real people? maybe. But I do think that that's part of the answer to making more realistic simulations. Like we do want to have, yeah, AI agents that are closer to real people in that sense.
Mm-hmm. So I have a question. Do you guys collaborate somehow with government representatives? Because, you know, like you come up with those like strategies, right? Like how to bring this to reality so the authorities can consider it and re-implement in real economy.
Yeah, I can't comment too much on like what governments like actually do, because you know to the extent that I know about it. But let's say that I've had, you know, that there's been interest. Like we've given talks at like nonprofits. We've given talks to, you know, we've spoken like with some non-governmental organizations. I think that part of this project, right, is sort of creating awareness among economists about the potential for these kinds of frameworks, right? Like, and to convince them that the use of AI can lead to better models of human behavior, to better policy optimization, and so on. But policy making is a very multilateral process, right? It just doesn't just involve technologists to come up with fancier algorithms and so on. It also depends a lot on you know, non-technical people, let's say, right, who really need to understand how this works. So I'd say that entire policy making process in the real world is quite complicated. And the way it works right now, right, is that, for instance, when the government in the U.S. Proposes a new bill that changes taxes or that subsidizes things, there are government and non-governmental organizations that predict the economic impact of those policies. So there's something called the Joint Committee on Taxation. There's the Tax Foundation. There's a number of these organizations that evaluate bills and evaluate laws that have been actually implemented. And so those organizations typically have economists and people who are more technical who will then provide advice to the government, right? So I think this process, in that sense, like it's about showing the potential of this framework to those economists. And I think that awareness is slowly building. So, you know, there have been some recent papers that have come out from central banks, for instance, that have documented some experiments with reinforcement learning that they've done themselves with some of their simulations. But I think it's just, you know, starting. And I cannot predict like at what, you know, when the government would actually take those models seriously. But what I do know is it's not like you just knock on somebody's door and like say, okay, here, why don't you use this, right? It's a much more complicated process. But you know, it's there. That's there for a good reason, right? And I think that's why this research is very exciting, because you do get to think about how your technology is used, and that's extremely important, right? To understand like if society actually takes these tools seriously and wants to use them in a responsible way, then what kind of requirements do you have for, you know, research or the things that you build, right? And I think that that's probably a very good thing to keep in mind for anyone who works in the technology space, right? To think about like, why is my tool useful, and like how does it actually benefit people who are not like, let's say technologists who just like get excited by algorithms. Like, you know, not everyone gets excited by algorithms. It's a shame, but you know, yeah, that's true. So yeah.
You know, I'm wondering, was there something interesting during those experiments that you didn't expect, that, you know, really surprised you?
Yeah, it's the tax schedules that were found. I think when we first saw that, we were also a bit surprised that you know, this pattern here in green. It's not something that we would have expected to come out of this. And I think that we're not saying that this should be used, right? It's just like this is what happens to be good in this particular simulation. But I think what is interesting is that there is this, you know, when we showed this to economists, some of them said, you know, it's counterintuitive, but it actually also to some extent makes sense because like the rates are very low in the middle, right? And so you could imagine that a very productive society gets as many people in that middle bucket as possible, for instance, right? So in that sense, there's different ways in which you can interpret what's happening here, and that's like very interesting because what that shows you is that it might be possible that these solutions that the AI system finds lead to new intuitions about what kinds of policies, what kinds of policy models would be effective, right? And so I think that kind of, I think to me that is just, it's to some extent surprising, but that we find this result. But I think that the process is very interesting. That basically this could actually, it piques people's interest a little bit, right? Even among economists. That's one surprising thing to me.
Yeah, thanks a lot. I encourage you guys to join our Slack, and I will post the video recording there. Also, Stephan, would it be possible to share your presentation with our community members? I'm pretty sure they would love to have it.
I'm not really sure if we've shared slides in the past. I can ask, but for now, I would say hopefully the video is enough to just like click through. I can ask, but we haven't really shared these slides, the raw material.
Okay, then we will just post the GitHub link, right, to your work, so people can.
Yes. So you can look at that, and we also have the paper. So I'll flash it here again. So yeah, the paper's on the archive. There's actually quite some material out there already about this.
Sounds great.